Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Look around you. The switch on the wall, the dashboard inside a car, a medical syringe barrel, a bottle cap, a fan blade. Many began as tiny polymer pellets. In this documentary, we will follow those pellets through heat, pressure, cooling, and precision tooling. But first, one question. How much production can a factory lose because an injection molding cycle becomes only 1 second slower? The answer is far larger than most people expect. Here is the answer. Assume an 8-cavity mold designed for a 30-second cycle and running continuously. At 30 seconds, it completes 1,051,200 cycles per year. At 31 seconds, it completes about 1,017,290 cycles. Multiply the difference by 8 cavities, and the loss is roughly 271,000 parts every year. This is theoretical output before downtime and rejects, but the comparison is exact. 1 second sounds trivial. Repeated across every cycle, it becomes a production strategy. To understand how to protect that second, we must first understand what the machine is actually doing. Injection molding can be understood in 3 verbs. First, plasticize. Heat and screw rotation converts solid pellets into a uniform melt. Second, shape. The screw moves forward like a plunger and forces the melt into a closed steel cavity. Third, freeze. Cooling channels remove heat until the part can resist ejection forces. The process is popular because the mold can reproduce complex ribs, bosses, textures, and snap fits at high volume. The machine supplies controlled energy and force. The mold gives geometry. The material supplies final properties. A modern injection molding machine has 4 cooperating systems. The clamping unit closes the mold and resists the force trying to open it. The mold contains the core, cavity, runners or hot runner, cooling circuits, and ejectors. The injection unit stores pellets, melts them inside a heated barrel, and meters the shot with a reciprocating screw. Finally, the drive and controller coordinate position, speed, pressure, and temperature. Choosing a machine requires more than shot weight. The mold must fit between the tie bars, the daylight and ejector stroke must be adequate, and the clamp must resist cavity pressure. Inside the barrel, the screw has 3 functional regions. The feed zone transports pellets. In the compression zone, decreasing channel depth compacts the material, while barrel heat and viscous shear melt it. The metering zone improves temperature and composition uniformity. During recovery, the screw rotates and moves backward as molten material collects ahead of it. During injection, rotation stops and the screw moves forward as a piston. Temperature must follow the specific grade datasheet. As one current example, Formosa's PE and PP guide gives a melt range of roughly 200 to 250 degrees Celsius, but engineering polymers can require much higher temperatures. The steel mold is not simply a hollow shape. Melt enters through a sprue, runner, or hot runner manifold, then passes through a small gate into the cavity. The core forms internal surfaces and the cavity forms external surfaces. Cooling passages remove heat, while vents allow displaced air to escape. After cooling, ejector pins, sleeves, or stripper plates push the part from the core. In a multi-cavity tool, balance is essential. Husky notes that all cavities should fill at the same time, because cavity-to-cavity variation reduces the usable process window and creates dimensional differences. This illustrative 30-second cycle begins with closing and clamping. The screw then fills the cavity in about 1.2 seconds. Packing continues for 4 seconds, replacing volume as the polymer shrinks. Cooling takes the largest share, 20 seconds in this example, and the screw can recover the next shot during that time. Finally, the mold opens and the ejector or robot removes the part. These times are not universal. Thin packaging can cycle in only a few seconds, while thick technical parts may take much longer. The lesson is that steps overlap, and one unstable step pushes every later step out of rhythm. During filling and packing, cavity pressure acts across the projected area and tries to separate the mold halves. The basic engineering relation is force equals average cavity pressure multiplied by total projected area. In this worked example, 40 megapascals acting over 800 square centimeters produces 3.2 meganewtons, approximately 326-ton force. Adding 10% headroom suggests a machine near 360 tons. This is an illustrative calculation. RJG advises including the projected area of cold runners and using actual cavity pressure information when available. Excess clamp is not automatically safer. It can reduce venting and waste energy. The cavity should first be filled under controlled screw velocity. Near the end of fill, the process transfers from velocity control to pressure control. This velocity to pressure transfer is one of the most important settings. Transfer too early and the cavity may not fill. Transfer too late and pressure can spike, producing flash or stressed parts. During pack and hold, pressure feeds additional polymer into the cavity to compensate for thermal shrinkage. Once the gate freezes, more holding time cannot change part mass. Processors often verify gate freeze time by increasing hold time stepwise until part weight stops rising. Cooling is where geometry becomes economics. BASF's analytical cooling equations contain the square of wall thickness. If all other conditions remain the same, increasing thickness from 2 to 3 mm raises the thickness term from 4 to 9, about 2.25 times. Doubling thickness from 2 to 4 mm raises it to 4 times. These bars are relative, not universal cycle seconds, because resin diffusivity and temperatures also matter. RJG explains why cooling can account for roughly 80% of a molding cycle. Uniform wall thickness and well-designed cooling channels therefore improve both quality and output. Injection molding is not one universal recipe. A 2025 Formosa guide gives a PE and PP melt window of about 200 to 250 degrees Celsius and mold temperatures around 15 to 50 degrees. BASF data for a glass-filled PA6 grade, Ultramid B3G4, recommends roughly 270 to 295 degrees melt, 80 to 95 degrees mold, and pre-drying at 80 degrees for 4 hours to very low moisture. Delrin guidance for standard POM grades gives an optimum melt temperature around 215 plus or minus 5 degrees and recommends a mold near 90 degrees for dimensional stability. These are examples only. Always use the exact supplier datasheet and verify measured melt and steel temperatures. A defect is a clue to the physics that went wrong. A short shot means the flow front stopped before filling. Investigate temperature, speed, venting, gate restriction, and available pressure. Flash means cavity pressure exceeded the mold's ability to stay sealed, or the parting line is damaged or dirty. Sink usually traces to thick mass, insufficient packing, or uneven cooling. Weld lines form where separated flow fronts meet and may be weak or visible. Warpage comes from unequal shrinkage caused by wall variation, molecular or fiber orientation, pack imbalance, or unequal cooling. Change one controlled variable at a time and preserve the evidence. A robust process is not a single magic set point. It is a window in which material, machine, and mold remain capable. Material variables include moisture, viscosity, lot changes, and regrind. Machine variables include actual injection velocity, transfer position, peak pressure, cushion, and timing. Mold variables include gate balance, venting, water flow, and steel condition. The output must remain consistent in part weight, dimensions, appearance, and mechanical performance. Record actual values rather than only controller settings. A process can display the same set point while delivering a different real melt temperature, cavity pressure, or flow rate. The cheapest defect is the one removed in CAD. Protolabs recommends keeping wall thickness as uniform as possible. Its guide gives a broad 1 to 4 mm range for many parts, while actual limits depend on resin and flow length. Begin draft around 1 to 2 degrees and increase it for texture or deep draw. Ribs can add stiffness without solid mass. A common starting point is about 60% of the adjacent wall thickness. Use generous radii at internal corners, core out bosses, and connect them with ribs. These rules reduce sink, stress, warpage, high pressure, and long cooling time before the mold is manufactured. Here is a practical output calculation. 8 cavities multiplied by 3,600 seconds per hour, divided by a 30-second cycle, equals 960 parts per hour theoretically. If overall equipment effectiveness is 85%, good output becomes about 816 parts per hour, or 19,584 parts in a 24-hour day. Stretch the cycle to 31 seconds and at the same OE, daily good output falls by roughly 634 parts. OE here is an illustration. Your plant should use its actual availability, performance, and quality. This equation turns process improvement into a number management can immediately understand. Injection molding is an economic trade. High upfront tooling buys low repeated cost. Consider an illustrative Indian rupee model. Suppose the mold costs 20 lakh rupees and injection molding costs 6 rupees per part, while an alternative process has no tooling charge but costs 20 rupees per part. The injection option saves 14 rupees on every repeated part. Dividing 20 lakh by 14 gives a break-even near 142,857 parts. This is a teaching model, not a quotation. Actual economics depend on cavities, tool life, resin, cycle time, OEE, scrap, labor, automation, maintenance, inspection and financing. Injection molding combines rapid mold movement, hot polymer, high pressure, electrical power, hydraulics or servo drives, and often a robot. Guards and interlocks must never be bypassed. Purging at the nozzle can eject hot resin, especially if material has degraded or trapped gas has formed. Maintenance requires site-approved lockout and tagout. Stop, isolate all energy sources, lock, release stored pressure or gravity energy, and verify the zero energy state before work begins. Robot and molding machine safety circuits must be integrated. Always follow the equipment manuals, the validated cell risk assessment, and your plant SOP. Modern injection molding is becoming more electric, instrumented, and integrated. Servo-electric drives offer precise simultaneous motion and power on demand. Arberg's energy guidance states that regular hydraulic machines can use twice the electricity of a modern electric machine, although the exact result depends on application and utilization. Hot runners can remove cold runner scrap. Cavity pressure sensors show what the melt experienced, while conformal cooling follows complex part surfaces. Automation handles and inspects parts consistently. A real Arberg application produces 32 two-component flip-top closures in an 8.5-second cycle, about 13,553 closures per hour theoretically. That output comes from optimizing the whole cell, not one setting. Let us return to the opening question. In our 8-cavity, 30-second example, one additional second removed roughly 271,000 parts of theoretical annual capacity. We now know where that second can hide: unstable material conditioning, poor screw recovery, an incorrect transfer, excessive holding, thick walls, weak cooling, slow motion or unplanned rejection. The engineering priorities are simple: prepare the correct material, fill consistently, pack only until gate freeze, cool uniformly, and measure quality, output, energy, and safety. Injection molding is not merely forcing plastic into steel. It is the controlled repetition of heat transfer, pressure, and motion, one precise cycle at a time.